Welcome to another podcast. In this episode, we're going to be taking a look at another improper integral. This time it's improper of type 2. And for improper integrals of type 2, remember that somewhere on the interval of integration we have an infinite discontinuity. And so that's what we're going to be looking for on this problem. And you can readily see that we have the infinite discontinuity at 1. You can clearly see it here. I'll try to draw in a line. Let's use a line of a different color here to show this vertical asymptote. So we have a vertical asymptote at the point 1. The function is approaching that vertical asymptote from both sides, and this is what makes this different than the previous problem. On the previous problem, we were only approaching the asymptote from the left side. Here we're approaching it from both the left and the right. So the idea is very much the same. We're going to look at the definite integral here on the left up to a value n, and we're going to let n approach 1. So we're going to let n approach 1 from the left. And then we're going to choose another value. Let's just call it b, I suppose. And we're going to let b represent the integral from 0 to 3, and we're going to approach 1 from the right. So remember, these one-sided limits always exist, so we don't have to worry about the limit breaking down. But we're going to approach it from each side here. And so this would be b approaches 1 from the right. Now, it's probably a good idea to use separate letters here simply so you don't confuse them if you have everything going on in the problem at once. So here's what I would do. My suggestion would be to create the integral from 0 to 1, since 1 is the point that is causing us problems here, and then add to that the integral from 1 to 3. So our integration rule says that we can do this very easily. And so what we've created here is not one type 2 integral, but now we have 2 type 2 integrals. So this first one I'm going to replace with the limit as n goes to 1 from the left. And the second one I'm going to replace with the limit as as b goes to 1 from the right. And so this would be the appropriate first step for these types of problems, just to make sure that you can write the integrals down correctly before you try to do any of the evaluation step. All right, if we actually try to evaluate this integral, let's start with the first piece. We'll have the limit as n goes to 1 from the left of the integral here is the integral of 1 over x minus 1 to the 2/3. So this is like x minus 1 to the negative 2/3. So using power rule, you add 1 to the power. That becomes a 1/3. And so you divide by 1/3, which is the same as multiplying by 3. So our antiderivative here is going to be 3x minus 1 to the 1/3. So if I use that, we're going to evaluate it at n and at 0. So evaluating it at n, we will get 3n minus 1 to the 1/3, minus evaluating it at 0, we get negative 1 to the 1/3. And so the b part here, we get the limit as b goes to 1 from the right of evaluating at 3, we're going to get 2 to the 1/3, minus evaluating it at b, we get b minus 1 to the 1/3. All right, so let's talk the limits of each of these pieces. As n goes to 1 from the left, then these are values that are smaller than n, so this value is going to 0 from the left. These are negative numbers that are approaching 0. So we're 0 from the left, but it doesn't matter if we're left or the right. 0 raised to a power is just going to be 0. So that whole thing's going to 0. And then the limit over here, we've got b approaching 1 from the right. So this is approaching 0 from the right. But once again, it's 0 to a power, so both of those go away. All that's left are these two terms that did not have any of the limit. This term is the cube root of negative 1, which is negative 1, times the negative 3. So we're going to get positive 3 from that term, plus 3 times 2 to the 1/3. And so our final answer is 3 plus 3 times the cube root of 2. And so because we actually got a value here, remember this means that the integral converges. So this is a convergent integral. It squeezes the vertical asymptote enough that we're not adding substantial area at the discontinuity point. And that's sort of the key idea in all of this is how quickly does this area squeeze down. The same thing with type 1 integrals, how quickly does the function squeeze down to its horizontal asymptote in that case. So both of these are similar types of problems. We're just looking at the rates at which the functions change. For this particular one, we did end up getting convergence. All right, so we've looked at type 1 and type 2 integrals. We're now going to look at some applications of those in future videos, so make sure you take a look at those. Thank you for watching.